continue with our discussion on stream function. So, the stream function we defined as a function of x and y with an understanding that it should satisfy the requirement of mass conservation constrained by the continuity equation, and special case is giving that parametric form, two dimensional incompressible flow. So, the important thing to keep in mind that it is defined for two dimensional incompressible flow in the way in which we are defining it. For other types of flows, special cases, again it may be defined with a slightly adjusted manner. Now, say we are interested to define it for a two dimensional compressible flow, but or a two dimensional steady flow, may be compressible, may not be compressible, but two dimensional steady flow. When you say a two dimensional steady flow, your continuity equation becomes whether rho is a constant or not, based on that it will come out of the derivative or not. So, this is a bit more general case than the case that we had considered, and for this also it may be defined, just replace u with rho u and v with rho v, then the similar parametric form may be defined. So, it is not that this is a hard and fast rigid definition, but this is like a definition for the most common case that we are talking about. Now, the stream function also has some relationship with the rate of flow. To understand that, let us say that we have some line element and we are marking 2 points 1 and 2. We are interested to find out what is the total rate of flow between these points 1 and 2. How we can do that? To do that, let us say that points 1 and 2 are located so closely that they are, or maybe let us consider a small element within that domain bounded by points 1 and 2. That small element is given by a length of dl, which is almost like a chord of this curve. Now, let us say that the length of this is dl. So, if you consider it like a vector sense, it has a outward normal vector like this, say n cap, and it may be expressed as a function of the important angles. So, if you mark this angle as theta, then you can write dl or decompose dl as dx dy. The length of this is dl. Let us say that b is the width perpendicular to the plane of the figure. So, it is possible to write this dl and subsequently dA, which is dl into b, as a function of like dx dy and the orientation given by the angle theta. So, dl in a vector form is like dl n cap. It is just like the area in a vector form is the magnitude of the area times the unit vector normal to the area and away outward to the area. So, here the area is represented by dl, b is the width, which is, so it is basically b into dl, that is the dA times the unit vector. So, the unit vector in terms of theta you can write, how you can write, say the tangent to the curve makes an angle theta with x. So, the normal to the curve makes an angle theta with y. So, how can you write n cap in terms of theta? So, you have to resolve the magnitude this vector with direction n cap and magnitude 1, because it is a unit vector in x and y components. So, the n cap is like this, it will have x component like this and y component like this. So, x component will be what? So, remember that this angle is theta, that means this angle is theta. So, x component is minus sin theta and y component is cos theta. So, b dl minus sin theta I plus cos theta j. So, this is basically the area. Now, if we want to find out the volume flow rate is nothing but what? The dot product of the velocity with the area, because if you have an arbitrary area, what will give rise to a volume flow rate? Only that component of velocity which is perpendicular to the area, that gives a net flow rate, right. So, if this is an area and the velocity vector may be arbitrarily oriented, but its component normal to the direction of the area is what is only important. That means dot product will give the component along that direction. So, the dot product of the velocity with the area vector will give the component of velocity along the area vector. Area vector means area normal. So, that will, the product of that will give the volume flow rate. So, the volume flow rate Q will be the this one B dl minus sin theta I plus cos theta j, this dot product with the velocity vector. What is the velocity vector? ui plus vj. It's a, we are assuming it's a two dimensional flow because we are discussing it in the context of stream function. So, everything is a two dimensional concept that we are discussing. So, what it will become? So, let us call it maybe dq, because we are talking about a small length, and the flow rate across this small length is expected to be small. So, the next step of simplification, it will be b dl times minus u sin theta plus v cos theta. So, you can also write it as b u into minus u into dl sin theta plus v into dl cos theta. From the figure you can clearly see that dl sin theta is dy and dl cos theta is dx. So, you can substitute dl sin theta with what? You can substitute this with dy, and you can substitute dl cos theta with dx. So, dq is b dl, sorry, b into minus u dy plus v dx. Okay. Try to find out its relationship with the expression for d psi that we derived just in the previous lecture. What was d psi? So, it was v dx minus u dy. So, this is nothing but b into d psi. That means if you want to find out the net flow rate between the difference in flow rate between 1 to 2, so dq from 1 to 2, that is b d psi from 1 to 2. So, the difference in flow rate between the points 1 and 2, q2 minus q1 per unit width is given by the difference in stream function. That means what is this q2 minus q1? q2 minus q1 is the net flow rate that is taking place through the element 1 to 2, because it is basically sum up of the flow rates over such differentially small elements like dl. So, q2 minus q1 is the net q across one 2. You can clearly see that if psi 2 equal to psi 1, that is if the values of the stream function are same, then there is no flow, and it is quite logical because we have defined streamlines in such a way that streamlines are such that the velocity vectors are tangential to the streamline. So a very important corollary of that is there cannot be any flow across a streamline. So if you have a flow, if you have a streamline like this, you cannot have any flow across this, because all the velocity vectors are tangential to it. There is no normal component of velocity, and normal component of velocity can only give a cross flow. So because it is so, you can clearly see that from the definition of stream function also it is reflected in that way, because streamlines are characterized by constant stream function. So you do not have a change in stream function along a streamline, and therefore no flow across a streamline. So the difference in stream function between 2 points gives a quantitative indication of what is the flow rate across a line element that joins those 2 points per unit width. Per unit width is important because it is just a 2-dimensional concept. So with this background on stream function, let us work out maybe 1 or 2 problems from your textbook related to stream functions. So let us work out maybe one simple problem to begin with. Say you have flow field given by the following components: u equal to 0, v equal to minus y cube minus 4z, and w equal to 3y square z. These are the velocity components which are given. Now the questions are as follows. Number 1, is the flow 1D, 2D or 3D? Perhaps you cannot have a more simple question than this. The next one, whether it is incompressible or compressible flow, and the third part is that if possible define a stream function for the flow. See, if possible is very important, because the stream function is not defined for all types of flow. So if that stream function is defined, then only find out the stream function. That is the whole idea of the problem. So let us try to work out this problem. So the first part, it is a 2-dimensional flow because it has 2 velocity components. Fine. Incompressible or compressible flow. So how will you test? The divergence of the velocity vector you should find out, because that gives the rate of volumetric strain. So if the rate of volumetric strain is 0, that means it is incompressible flow. So we have to check what is the divergence of the velocity vector. So here it will boil down to the checking of what is this. So the first one is minus 3y square and the second one is plus 3y square. So this identically becomes equal to 0. That means it is incompressible flow. So now you have a 2D flow from the first part, you have an incompressible flow from the second part. Since it is 2D and incompressible, the stream function itself is defined. So we can now attempt to find out the stream function. How do you find out the stream function? So now it is like it is in a YZ plane that we are talking about the flow. So you have to define in some way V and W in terms of the stream function. So how do you define V? Maybe again plus minus sign is not that important. What is most important is it should be of opposite sign to make this equation trivially satisfied equal to 0. So let us write the corresponding components. Yes.
This is a different V. We are having one V component.
Yes. This is a V component, this is a W component. So these are written in such a way that this equation is satisfied. That is what I am always saying, that don't write, take it as a formula. Now see that with a slight change the components of velocity given as y and z components instead of the previous ones, you see that you are facing a dilemma. That should not be there. Again the objective will be that given a form of the continuity equation, just write a parametric form which satisfies it, and that will automatically give you the definition of the stream function for that case. So do not confuse it with the case which we were discussing for developing the theory in the flow in the xy plane. Now the flow is in yz plane, so that definition does not work here. So this is given by minus y cube minus 4z. So if you integrate this with respect to z, what will be psi, yes, minus y cube z minus 2z square, then plus some function of y, because again repeating this is partial integration with respect to z. So when you are integrating with respect to z as a variable, even y is a constant with respect to that. It cannot be function of x here because there is no dependence of x. I mean x is just like it's a flow taking place in the yz plane. So where does the dependence of x comes? So you have to understand it physically. Then next here, so that is minus 3 y square z. So if you partially integrate with respect to y, so psi will be y cube yes, sorry, this is plus, right, psi equal to minus y cube z plus function of z. So you have say this as equation number 1 and the equation number 2, both are representing the same psi. So you have to compare 1 and 2 to get f1 and f2. So 1 and 2 are the same. So if you compare 1 and 2, what follows? What is f1y? It may be some constant at the most, and what is, or you may choose your reference in such a way that the constant itself is 0. Let us just keep it as a constant and see that how you can choose it to make it 0. And what is f2? f2z is minus 2z square. So the expression for the stream function becomes minus y cube z minus 2z square plus some constant. Now this constant you may arbitrarily choose because there is no absolute value of stream function, so to say. You have a reference, with respect to that you find out a change, because see the velocity component is defined as the partial derivative of the stream function. So it is not defined on an absolute sense with respect to the value of the stream function. So if you have the value of the stream function defined arbitrarily, say you define that your reference or origin is such that at y z equal to 0 psi equal to 0. Remember, it is not a must, it is just your choice, and always such choices are convenient because then you come up with that expression which will have c equal to 0. It does not matter whether c is any arbitrary value or not, because at the end difference in stream function is what is important, that c will get cancelled if you find out the difference in stream function. But for working convenience you may set your references in that way. In most practical purposes you have flows on solid boundaries. Usually the solid boundaries are considered to be, so solid boundary itself is a streamline, right, because there is no flow across it. So by its physical sense any shaped solid boundary is itself a streamline. So you can give it a value of a particular stream function if it is a 2-dimensional incompressible flow. So classically, just as a matter of convention, we give it psi equal to 0 as a reference. Again there is no sanctity with it, you might give 1, 2, 4, 5 whatever, but it is just a reference, a datum with respect to which you want to calculate other stream functions. So solid boundaries are classically referenced as zero stream functions. So let us maybe move on to next problem, which may be similar to this, but let us just work out another problem with respect to the concept of the stream function. So to do that, again we will be solving a problem from your textbook.